Hello and good evening. It is my great pleasure to introduce the Block Community Lecture, which is one of SCIAM's signature lectures at the annual meeting. It's named in honor of Edward Block, who was a co-founder and former managing director of SCIAM. And the IE Block Lecture is given annually at the SCIAM annual meeting. And if you're not a SCIAM member, SCIAM is not a country in Asia. We are the Society for Industrial and Applied Mathematics. And this lecture is open to the public. It will also be live streamed on our YouTube channel and recorded. And the lecture is really meant to encourage public appreciations of the excitement and vitality of science. And tonight's speaker really embodies this vitality and excitement for mathematics. So it's my great pleasure to introduce Kiva Rooney from Aeroscale and Mathematicals, who will give her block lecture in a moment. And she's currently really living the dream of an applied mathematician by working on fun applications. She obtained her undergraduate degree from the Trinity College in Dublin and a Doctor of Philosophy in Applied Mathematics from the University of Oxford in England. Dr. Rooney began her research as a scientist at NASA and working on modeling techniques to study exoplanet electromagnetic spectra, aiming to understand their composition and potential for life. So she was looking for life outside the solar system, which is really cool. And then she started doing something which is even cooler. She joined Aeroscale, motivated by a passion for ensuring the accessibility of space for future exploration. And there she works on the design, development, and operation of in-orbit services, spacecraft to remove space debris. She's won numerous awards. She's on the Forbes 30 Under 30 Europe list. She co-founded Mathematicals, which is an educational initiative to make math accessible and promote representation of women in STEM. And so I'm really excited to go with all of us boldly where no math has gone before. And so at this point, I'm going to beam myself off stage and hand the bridge over to Captain Rooney to take us on a voyage of discovery. Kiva Rooney.
Okay, hello. Thank you, Sven, very much for that very kind introduction. I am absolutely delighted to be here giving the Block Community Lecture. It's really an honor to be asked, and I hope that I can do justice to the heritage of the lecture and also to the legacy of Ed Block, after whom the lecture is named. So my talk is titled, Go Boldly Where No Math Has Gone Before. And I'm hoping to take you on a bit of a mathematical journey, talking about the way math defines the world around us, but also how it continues to be essential in the innovative technologies advancing us into the future. So this slide has been stolen by Sven, but it outlines my career kind of so far, bringing me to where I am today. So my undergraduate was from Trinity College in Dublin in pure maths, so looking really at the fundamental concepts of mathematics. I then moved on to do my PhD in applied maths, and the program I was on was called Industrially Focused Mathematical Modeling, and it was aimed at trying to bridge that gap between academia and industry, so very much encompassing the ethos of SCIAM. And I worked on metallurgical furnaces, trying to see if we can manipulate materials to be more suitable for industrial processes. And it was really there where my love of applying maths to different ways we can solve problems was sparked. I've always loved space, so following my PhD, I achieved a postdoc at NASA Ames in California, and that's where I was looking at exoplanets. So for those who aren't familiar with what an exoplanet is, it's a planet far outside of our solar system, too far away to visit. So the only way we can understand them is by looking at the data picked up from telescopes. And that data comes in the form of electromagnetic spectra. So I was using mathematical modeling techniques to try and understand what defines that spectra, what elements and different things within the planet's atmosphere could possibly produce the spectra that we were observing, and ultimately with the hope of finding life. I'm currently a flight dynamics engineer at Astroscale, which I'm going to talk a bit more about soon. As Sven mentioned, I'm a co-founder of Mathematicals with my colleague and friend Jessica Williams, because we're passionate about trying to communicate maths to the general public and encourage more children, particularly young women, to get involved in maths and also banish that stigma that maths is not interesting or that it's boring. And finally, I am really hoping to one day maybe go to space myself. So I've been training as a citizen scientist astronaut in the hope that that might one day become an opportunity. So why am I here? When I tell people that I'm studying maths or I'm interested in maths, I often get faced with the same sort of responses, that maths is boring or it's useless. Some people will say maths isn't for everyone, you have to have a certain type of brain to be able to do maths, that you have to be really smart to even start to attempt to do maths. And people think maths is just about doing very quick sums in your head and multiplying numbers quickly, which I'm not good at. And a lot of people would be disenchanted with the maths they learned in school, not really knowing where that's used in everyday life. So there's sort of this general misconception that maths isn't useful or interesting. And I'm hoping through this talk that I can change that a little bit and sort of talk a bit about the interesting applications of maths, and in particular, how I use it to solve things that I'm fascinated by. So what am I going to talk about? So the first thing I'm going to do is recall some topics and applications that you might be familiar with. I'm going to focus on 3: probability, trigonometry, and geometry. So hopefully things that you've heard of and maybe even studied a bit in school. And then I'm going to introduce the problem of space debris, which I currently work on, and in particular explain how these mathematical concepts that I've discussed are critical in the area of active debris removal. So let's get started with probability. Everyone's probably quite familiar with what probability is, but in a nutshell, it's how likely something is to happen. One of the most familiar ways that probability is used in our everyday lives is in weather forecasting. So we're all affected by the weather. We want to know what the weather's going to be like today, tomorrow, in a week's time. We want to know whether to pack a rain jacket, put on sun cream. And when we open our phones, we've got access to all of this information right at our fingertips. So precipitation, UV index, temperatures, and all of that is underpinned by probabilistic models. And in particular, if you're coming to Washington as an Irish person, you really need to know what to expect in terms of temperatures, because it's really not safe for me here. Another application that sort of extends beyond the everyday life is that entire industries are founded upon probability. So an example of this is the betting and sports betting industry. And this can bring in a lot of money and a great amount of revenue. So for example, in the US in 2023, sports betting brought in $11.04 billion. So probability can be quite profitable. And the probability behind sports betting comes down to odds, and odds are based on the likelihood of things happening. So all of these things are uncertain and can be described by the probability of a particular outcome occurring. And finally, another prominent application of probability is in healthcare. So we were all very aware of the COVID-19 pandemic. We were surrounded by plots and graphs showing the spread of the virus, the number of deaths, and projections as to how that might evolve over time. And probability models were used to predict potential outbreaks and to look at the effectiveness of different mitigation strategies, such as quarantines and masks and vaccines. And these probability models really help to inform government and the general public as to how to respond to try and stop the spread of the virus and ultimately save lives. But in general, probability is applied in healthcare all the time. We're always talking about the likelihood of an outcome, how effective we expect a medicine to be. And critical medical decisions are based upon probabilistic outcomes. So I'm hopefully going to show a video now that's going to demonstrate a bit of the fun side of probability, but also how some probability can be used in game theory.
welcome to the Mathematicals Show, with me, your host, Marty Hall. Please welcome today's contestant. Give her a huge round of applause.
Thanks for having me on, Marty.
Here's how the game works. You'll see we have 3 doors. Behind 2 of the doors are goats, and behind the 3rd door is something you really desire. Let's say, equal pay for women.
So I just guess which door I think equal pay for women will be behind?
Exactly. Now, which door do you choose?
Marty, I choose door number 1.
An excellent choice. But before I reveal whether you're correct, I'm going to give you one chance to change your mind. Let me show you that behind door 2 is a goat. Do you want to stay with your original guess of door 1 or switch to door 3?
Although intuition might suggest I've got a 50-50 chance of winning either way, if we look more carefully, we'll see that I'm actually more likely to win if I switch to door number 3. Let's look at why that's the case.
Here are our 3 doors, and we initially picked door number 1. There are 3 possible scenarios as to where the prize is. It could be behind door 1, behind door 2, or behind door 3.
In the first scenario, we guessed correctly. But remember, we don't know that yet. The host will either open door 2 or 3 to reveal a goat, but either way, we'll win if we stay, but lose if we switch.
In the second scenario, where we pick door 1 but the prize is behind door 2, the host will open door 3 to reveal the goat, so we'll lose if we stay but win if we switch.
In the final scenario, where we picked door 1 but the prize is behind door 3, the host will open door 2 to reveal the goat, so we'll lose if we stay but win if we switch.
Tallying these up, staying will result in a win in one of the 3 scenarios, whereas if we switch, we will win in 2 of the 3 scenarios.
That's equivalent to saying the probability of winning if we switch is 2/3, and the probability of winning if we stay is only 1/3. So in general, it's a better tactic to switch than stay.
This problem is known as the Monty Hall problem, and it gained a lot of attention in the 90s.
Marilyn Vos Savant, a woman listed in the Guinness Book of World Records for having the world's highest IQ, established Ask Marilyn, a weekly column discussing a variety of academic questions and logic puzzles.
In 1990, Marilyn devoted one of her columns to the Monty Hall problem and correctly explained that switching doors would maximise your probability of winning.
She used the analogy of having 1 million doors, and after picking door number 1, the host, who knows where the prize is, opens every other door except for, say, door number 777,777. You'd probably feel safer switching to this door than staying with your initial 1 in a million chance choice, right?
However, she was met with the wrath of outraged academics claiming she was wrong. In fact, she received more than 10,000 letters, nearly 1,000 from those with PhDs, all to the tune that she was entirely incompetent.
They were all convinced that once the choice was down to one of 2 doors, it had to be a 50-50 chance. It's clear that I've got the best chance of winning if I switch. I'll go with door number 3, Marty.
Door number 3 it is. Oh, but it looks like we're all out of time. You'll have to tune in next time to find out if our contestant has won.
Okay, so that's an example of some of the outreach videos that Jessica and I make through Mathematicals to try and showcase how probability is useful, but also try and make it a bit more fun. So going back to probability, how did probability become to be this fundamental topic that defines so much of the world around us? Let's talk about some of the mathematicians behind the development of this field. So some of you might recall George Boole, or maybe you're more familiar with his work, Boolean algebra, which is the maths behind the modern computer. It's captured in his well-known book, The Laws of Thought, from the 1850s. And not only is it the math behind computers, it's also the foundation of many other probabilistic theories, including Bayesian statistics. So those of you that maybe studied probability to university level or have done a bit of statistics, you might be familiar with Bayes' theorem, which describes the probability of something occurring conditioned on another event. We also have Carl Gauss, who, among other notable mathematical contributions, is known for coming up with the Gaussian distribution, or the bell curve, or the normal distribution, which is one of the most fundamental concepts in probability and statistics. Within the formula for the bell curve, you'll see the letter E, which is the Euler number, named after Leonhard Euler, who is known for a multitude of mathematical progress, but devoted a large portion of his career to the calculus of probability. And then finally, we have John Venn, who came up with the diagrams that a lot of us would be familiar with for expressing different probabilistic outcomes. He was also highly influential in developing the field of statistical theory. So those are names you might know, and there's names that theorems have been named after, and different concepts have been named after. But I'm going to talk about a couple more mathematicians who also contributed to probability theory that you might be less familiar with. So Mary Everest Bill was married to George, and she was a self-taught mathematician, and she actually advised her husband when he was writing his book, The Laws of Thought, and also attended his lectures, and that was unheard of women at the time. She had quite progressive ideas on education, and she wrote her own books, including one called The Preparation of the Child for Science, and Philosophy and the Fun of Algebra, encouraging children to engage and explore mathematics in playful ways. Sophie Germain was interested in maths from when she was a child, even though she was discouraged by her parents. And she actually interacted and corresponded with Carl Gauss under the pseudonym of M. Leblanc. And eventually he discovered her true identity, and he discovered her gender, and wrote that she had the noblest courage, extraordinary talent, and superior genius. And Sophie is known for her work towards proving Fermat's last theorem. We have Emily de Châtelet, who's best known for her translation and commentary on Isaac Newton's Principia. And she also corresponded with renowned mathematicians such as Bernoulli and Euler himself. And then we all might be more familiar with Florence Nightingale, who's the mother of modern nursing, but also a distinguished statistician. So Florence used polar area diagrams to communicate complicated statistical reports to government, reports that would otherwise be ununderstandable to those people. So through that, she was fundamental in using statistics and probability to encourage social reform. She was the first female elected to the Royal Statistical Society. So not only have these women contributed to the development of probability and the development of mathematics, but pay particular attention to the emphasis they put on translating these topics to government, to children, and just to a wider audience, and the part they played in making sure that these concepts became accepted and used. Okay, moving on to trigonometry, which in essence is the relationship between angles and triangles. We're all pretty familiar with Pythagoras. I can imagine everyone's probably had to deal with right-angled triangles sometime in their lives. Maybe you still recall some of the formula that you were forced to memorize, sine, cosine, tan, and you might even have the word hypotenuse burned into your memory somewhere. But where does that come into the life that we lead? Where does that come into the world around us? So one such example is game design and computer graphics. So trigonometric functions are used to define paths, circular, smooth curves, and movements of characters. We use trigonometry to project 3D images onto 2D scenes, to calculate shadows and different lighting. We also use trigonometry and collision detection, and that's something I will actually talk about a bit more later, because that expands a couple of different fields. But all of these things use trigonometric identities, the ones that we're familiar with. Astronomy is one of the oldest applications of trigonometry. It's been used throughout history to try and understand how far stars are away. A concept called stellar parallax uses trigonometry by observing a star at 2 points during the Earth's orbit, 6 months apart, and seeing the shift in how that star moves against background distant stars. We can measure the distance using trigonometry. We can calculate the size of celestial objects using something called the angular diameter, which is using trigonometry, and the Doppler effect, which is crucial to understand the motion of objects, celestial objects, and that's all founded upon trigonometric relationships. And then finally, something that we're a bit more familiar with and that we also use, well, I certainly use, all the time, is GPS, trying to get from A to B. I would be lost without Google Maps. And that, at the core of that, is trigonometry. So GPS technology involves a technique called trilateration, and that involves with satellites and the network of satellites that define GPS, having a distance from each of those satellites, understanding how those distances interact with each other and radii intersect. The intersection of spheres and triangles helps us to pinpoint exact locations on the Earth's surface. And staying on GPS for a moment, you might be familiar, or maybe you don't know, about a woman called Gladys West. And she was pivotal in the development of GPS technology and for improving its accuracy. So for GPS receivers and our phones to be able to calculate distances to the satellites, we have to have very accurate predictions of the satellite's orbits. And satellite orbits are very dependent on the Earth. So we know the Earth is not a perfect sphere. And it's described as an ellipsoid, but even more than that, it's quite irregular. And its surface is defined by tides and gravity and mountains and things. And these can be very impactful on the orbit of a satellite. So Gladys was involved in deriving more accurate models of the Earth, describing the Earth's surface as a geoid, and in doing so was able to refine the models that we use to predict satellite orbits, and therefore becoming a very important person in making our GPS modeling as accurate as it is today. And trigonometry is actually a subset of our next and final subject, which is geometry. So going beyond just triangles and angles, geometry includes points, lines, surfaces, and solids. And it's one of the oldest mathematical branches, dating back as far as the 2nd millennium BC. Throughout history, it's been used in construction, surveying, and astrometry, calculating areas and volumes. And you might recall from school doing geometry and using compasses and protractors, drawing circles and measuring angles. But how is geometry used in our everyday lives? And like probability and trigonometry, there's quite a lot of applications that impact us all. So an obvious one of this might be design and structures and building and architecture. But I want to draw your attention to the image on the screen, which is the Walkie-Talkie building in London, and it's noted for its unusual shape. But what happened when this building was erected was that the building's curved, reflective facade focused light into a very pinpoint area on the streets below, causing temperatures to go as far up as 243 degrees Fahrenheit, causing parts of cars to melt and for the pavement to be scorched. So the geometry of the Walkie-Talkie building demonstrates that we can use geometry to produce striking and innovative designs, but we have to be careful because such geometries could have impact beyond just aesthetics. Another example is the Jabalani soccer ball from the 2010 World Cup. So it differed from a traditional football in that it wasn't bound together by stitched panels. It was thermally bonded to try and create a nearly perfect sphere, which you might think would be perfect, the best that you could possibly have for a football. But what the players found and what they complained about, particularly goalkeepers, was that it was very difficult to predict the trajectory of the football. It was different to what they expected. Scientific studies were conducted, particularly studies in air tunnels, showed that because of the lower air resistance of the football, the trajectories and the flight path were more pronounced than what was expected. And this resulted in more erratic behavior. So the aerodynamics, this perfectly aerodynamic sphere, actually caused such controversy that it became one of the least favored balls to be used in a World Cup. And then finally, medical imaging, something that also might affect a lot of us in our lives, relies upon geometry. In particular, CT scans use X-rays to study internal organs in 2D images, and then mathematical geometrical models are used to construct those into 3-dimensional images and help doctors to diagnose conditions and to get a better understanding of internal structures. So what about me? I've just talked about some mathematics that you might be familiar with. I've talked about how other people have used these and brought them into technology around us. During my studying and my career, I've also applied mathematical techniques such as these to concepts in fields like blenders, trying to make your smoothie as smooth as possible, metallurgical furnaces, like I mentioned, exoplanets, and now space missions. So these apparently simple and very fundamental concepts are critical in solving some of the world's most challenging problems, including the issue of space junk. So what is space junk? Space junk, also known as space debris, are defunct human-made objects in space. And this can include things like derelict satellites that no longer work, bits of old rockets, mission-related debris such as tools that maybe astronauts have dropped while operating on the side of the ISS, fragmentation and debris, so bits of broken things from collisions or from derelict objects breaking up in space. And as of 2021, we have 7,500 working satellites, 2,040 discarded rocket states, 2,800 defunct satellites, 21,000 other bits of debris, 26,000 to 28,000 tracked objects, so we know where they are, and 365,000 objects larger than 10 centimeters. And why do we care about this? Well, having so much in space makes access to space difficult, and it means when you're in space, you're at risk of collision, particularly the astronauts and the ISS always having to do maneuvers to avoid bits of debris. So taking a quick look at the history of space junk, the beginning of space exploration really happened in the 50s with the launch of the first artificial satellite, Sputnik. Within the 70s, we're already having growing awareness of the potential risk of overcrowding space with something called the Kessler syndrome, which I'll come back to. In the 80s, we were already seeing an increase in debris through the Space Shuttle program, the explosion of the Challenger shuttle. We were starting to see major collisions take place in the 90s, collisions of satellites with debris and also satellites with bits of rocket body. This continued into the 2000s. We had China do a missile test on its own satellite, creating debris. And then we had a collision with a Russian satellite and a US satellite. And from sort of the early 2010s, we've had rising concerns. So the UN has stepped in with space debris mitigation strategies. We've had other collisions. We've had space companies and private space companies and space nations trying to get together to think, how can we solve this problem and test different technologies? So let's just hone in on a couple of these points. So what is the Kessler syndrome? So this is a theoretical scenario in which the number of objects in low Earth orbit is high enough to cause a cascade of collisions. So what that means is when one thing collides, it creates more debris, and this ongoing effect is that we have so many collisions that the debris sort of grows exponentially to the point that space missions are at risk and access to space becomes more difficult. If we look at some of the collisions in this timeline, we see that the collision with the French satellite Cerise and a fragment from a defunct Russian satellite was one of the first major collisions. The collision between the Russian satellite and the US satellite created 2,300 bits of debris trackable and was the first accidental collision in space. And China's anti-satellite mission test to destroy one of its own weather satellites actually increased the space debris at the time by 25%. So even single events can have catastrophic impacts on the space debris landscape. And then legal and policy members. So we are trying to do something about this. The Outer Space Treaty of 1967 and the Space Debris Mitigation Guidelines by the UN aim to mitigate the creation of debris. And we have space agencies increasingly incorporating mitigation strategies into mission plans to try and avoid the problem growing. But then we have companies dedicated to strategies such as active debris removal and in-orbit servicing to tackle the problem that already exists. So what is active debris removal? So let's go back, bring our earlier concepts of probability, trigonometry, and geometry, and talk about how each of these are critical in active debris removal. So first of all, what is it? We have several strategies to mitigate the risks of space debris that pose an issue or a risk to future space exploration. One of these strategies is known as active debris removal, and it involves techniques to capture and remove large pieces of debris from orbit. So Astroscale, the company that I work for, is partnering with national space agencies and international organizations to research and develop missions that incorporate solutions to capture and remove existing debris. So how do the maths that I've mentioned come into play here? How do those three simple concepts play a part? Let's start with probability. So I've already mentioned that there's around 28,000 pieces of trackable objects in space. And the general concept is that we should know where everything is and where it's going to be in order to make sure that none of these are going to collide. And in our case, we have a spacecraft orbiting Earth. So it's our duty and our interest to know where we're going to be, to predict our orbit, and make sure that we're not going to hit anything, compare our orbit to the orbits of other bits of debris, and make sure we won't hit anything, and if we will hit it, make sure we get out of the way. So how do we do that? So let's start with our own spacecraft there on the screen. So we use mathematical models founded upon orbital dynamics to predict our trajectory. And we can do that with fairly good accuracy. We know where our spacecraft is going to be on its journey. And then we compare this orbit, and we compare this path to the trajectories and orbits of other things in space to make sure that we're not going to hit anything or there's nothing going to be in our way that could pose a risk to our craft. However, orbital dynamics are complicated. It's difficult to model accurately. And in particular, the space environment that we're in is complicated. And our spacecraft will be exposed to lots of natural perturbations, such as atmospheric drag, solar radiation, gravity. And all of these things mean that our orbital trajectory is imperfect. So to account for these perturbations, when we're looking for things we might hit, we just expand our search region a little bit. So we don't just look at our trajectory, but we look at the area around it, searching for objects. Another issue is that our orbital predictions get worse with time. So as we look further into the future of our trajectory, our predictions are more uncertain. And we account for this uncertainty by expanding that search region even more. And we can see in this schematic that there's an unsuspecting satellite has found itself in our danger zone. So we use our trajectory prediction along with our uncertainty estimates to calculate a collision probability with other tracked objects in space. So it's very important to be able to calculate the probability of collision accurately because we want to be careful. We want to be safe and careful and cautious, but we also don't want to do any unnecessary maneuvers because doing too many maneuvers unnecessarily wastes fuel and can also pose a risk to space missions. So as we mentioned, we can predict the spacecraft's position using mathematical models, but due to the uncertainties of the environment, it is uncertain, and we have to account for that. And the way we do that is with things like probability density functions, and they're used to capture these uncertainties by not just considering a single deterministic point, but a range of possible outcomes. So instead of thinking we're definitely in this position, we could actually be in a range of positions quite close to that based on our uncertainty. So what is a probability density function? Cast your minds back to Gauss, who came up with that Gaussian distribution. That's an example of some of the probability density functions that can be used to model positional uncertainty in spacecrafts. So in simple terms, if we consider where we think our spacecraft is, we defined an uncertainty region. So that could be a sphere surrounding our satellite, meaning that we could technically be anywhere within that sphere with different levels of probability. We apply that same logic to other objects in space. And then in determining whether we have a risk of collision, we look at whether the two spheres of our craft and other things in space are going to overlap. And then we calculate the collision probability, which is the likelihood that a collision will take place based on sort of how much these spheres overlap. And there's many different ways to calculate this probability collision. There's a lot of research goes into this, and there's differing pros and cons for each method that can range from computational efficiency to also numerical accuracy. Okay. So once we're certain that we're not going to collide with anything, we want to start to turn our attention to actually catching up with a bit of debris. So when we're far away from the thing we want to catch, we have to figure out our position relative to that. And we can't see it. We can only start to try and take pictures and try and get closer to it through that. So I'm going to introduce two vectors. The first is a pointing vector, which is the direction that we're pointing. And we know this because we command it. And then I'm going to label the thing we're trying to catch, that bit of debris, it's the client. So our second vector is the line of sight vector to the client, and that describes the direction of the client with respect to us. And we want to determine this vector, and we do that by taking images in space. So we'll take an image, and as I said, we're very far away, so you won't really be able to make out exactly what the client looks like. It'll only appear as a collection of pixels in your image. And so although we can't work out the size or the shape at that time, we can work out its position relative to us through this line of sight vector. And we capture that through two angles. So let's make this a little bit more mathematical and turn our system into a coordinate system. So we have the z-axis is our pointing direction. So that's the direction where we're looking. And then we'll define the x and y axis as our perpendicular axes. And then our line of sight vector, the vector that we can determine from the image, is a unit vector in this coordinate system. So to determine the relative direction of the client, we want to calculate two angles, the elevation angle and the azimuth angle. So the elevation angle essentially describes how much above or below us the client is. And we can do that by projecting our line of sight vector down onto the zx plane and calculating that angle, which is the same as looking at this triangle you see on the screen. So the elevation angle is measured from the xz plane up to the line of sight vector. The azimuth angle, on the other hand, is how to the left or to the right of us the client is. And similarly, we can draw a triangle from our coordinate system to try and find that azimuth angle. So what you'll see on the screen now are two right-angle triangles, which you all studied in school, and you all know the equations as how to calculate those. So this pretty complicated problem of finding something in space boils down to those very familiar and fundamental trigonometric identities that we were talking about earlier. So the issue, though, with this method is that we can easily determine, or we can somewhat determine the relative direction in these two angles, but it can be difficult to determine how far this client is away from us. And that's because the line of sight vector is not really unique. So if we have an image, and we have pixels on that image, and we can figure out, okay, with respect to me, the client's over there, I can't tell if it's this far away, even closer than that, or even further away. And the method that I've described, this technique that we use, is called angles-only navigation. So its acronym is AON, and it's used to determine the position and motion of an object relative to an observer by using only angular measurements. And we observe that from different positions, so our elevation angles and our azimuth angles change, providing information about the target's relative motion. And we use algorithms and mathematical models to compute the client's trajectory. But it can be difficult to deduce that range, and that's actually called a range observability problem. And that's because we have this non-uniqueness in terms of the line of sight vector. But there are different ways we can improve this. The first one would be to consider measuring angles from more than one camera. So the example I used was taking a single image. If you had two cameras taking images, you can get more measurements, and that can help you also determine the range. You could also install the camera away from the center of mass of the spacecraft, and that again is just allowing for some more diversity in your measurements. You can execute maneuvers during imaging, and that again is just increasing the diversity of the measurements that you're getting throughout your mission, or mathematical modeling in the solution algorithms. So the first two are kind of hardware solutions that we have to do that before we get up there, try and fix, put the camera in the correct place or put more cameras on the craft. The third one is a mission solution. So when you're planning the mission, you might want to plan these maneuvers to make sure that we have the diversity that we need. But that can be complicated as well in terms of fuel, or if your maneuvers are happening when the sun isn't in the right direction, you're not getting the same visibility that you would have, that can be an issue. Which is why we're interested in the mathematical modeling solution, and that is that mathematics can be essential in trying to improve these algorithms that help us catch up with objects in space. Okay, so we've spoken about probability, we've spoken about trigonometry, but what about geometry? So geometry is the foundation of orbital dynamics, which is used to understand how our spacecraft actually moves around the Earth. So to catch up with a bit of debris, we need to match the orbit of that debris. And in order to do that, we need to understand what defines a particular orbit. So although we can have circular orbits, it's quite likely that orbits are actually elliptical, with the heavier body involved being at one of the foci of the ellipse. So an ellipse has two foci, and in the case of something orbiting the Earth, the Earth will be positioned at one of those foci. We can define some important parameters that help explain the size and the shape of our orbit. And one of those is the semi-major axis, and that is used to describe the size of the orbit. It's defined as the half-length of the longest diameter of the ellipse. We can also define the eccentricity, denoted by the letter E, and that describes the orbit shape. So if an orbit has eccentricity 0, it's going to be a circle, and then an elliptical orbit will have eccentricity somewhere between 0 and 1. There's also two very important points of an orbit, the perigee and the apogee, which are the closest and farthest points from the Earth, respectively. And then as something moves around the Earth, we will describe the orbital period of that body. So that's the time it takes to complete an orbit. And it depends on our semi-major axis, A, and also on another constant called the standard gravitational parameter. So we know its shape, and we know its size, but we can take another view of the orbit to try and get some other parameters to help us understand its orientation. So to understand the orientation, we define two planes. We have our orbital plane, which is the plane on which we orbit the Earth, and a reference plane, which for things orbiting the Earth is often taken as the equatorial plane. And there are a number of important parameters needed to help define the orientation of our orbit. The first one of these is the inclination. So that's the angle between our orbital plane and the reference plane, or the equatorial plane. We have another parameter called the longitude of the ascending node, and that determines where our orbit crosses the equatorial plane. And we have another angle known as the argument of periapsis, and that describes the orientation of the orbit with respect to something called the line of nodes. And that line of nodes is that line of intersection between our two orbits. Okay, so now we know the different parameters that we need to describe an orbit, the shape, the size, the orientation. How do we go about actually catching up with something? So as I said, if we wanted to catch up with an object in space, we have to try and get on the same orbit and then get closer. Before we dive into space, let's think about what that means on Earth. So I want you to imagine that you're driving a car along a straight, flat road, and you want to catch up with the car in front of you. People are probably familiar with the fact we're moving in a particular direction. Our velocity direction is pointed in that direction of travel, and if we want to go faster, all we do is put our foot on the accelerator, accelerate in the direction of travel, and we will move closer to the object that we're trying to catch. But now let's think about space. So imagine we're on the same orbit as the client, the thing we're trying to catch. We've managed to get to that point where we're on the same trajectory, but we're still just a little bit too far away. The consequences of the rules of orbital dynamics can be a bit counterintuitive, and if we wanted to try and move closer, we can't just accelerate the way that we would on Earth, unless we're very close. If we were to do that, what would happen is actually that we would change the shape of the orbit. It would cause us to increase our altitude and actually slow down with respect to the thing that we're trying to catch. So in this case, if we fired our engines in the direction that we're traveling, we would just create an orbit of a larger semi-major axis, and we would no longer be on the same trajectory as the client. So this is called an orbital maneuver. And trying to catch a piece of space debris normally involves many precisely calculated orbital maneuvers over multiple days, months, to be able to actually match that orbit and catch up. So there's lots of different types of orbital maneuvers for this purpose. There's the Hohmann transfer, so that's a two-burn maneuver. So you would burn your thrusters at two different points on your orbit, and that would be used mostly to try and transfer between orbits at different altitudes. Bielliptic transfer sort of does the same thing, but with three burn maneuvers, and it's useful for when you're trying to have larger changes in altitude. It's potentially more efficient. And we talked there about changing the shape of an orbit, but what happens if you wanted to change the orientation? You would do something called a plane change, and that would adjust your inclination. When you actually do manage to get close enough, we want to catch it, we want to grab it, and that's called rendezvous and docking, and that will be a series of smaller maneuvers to try and bring two spacecraft close enough that they could actually dock. And then finally, when you want to leave Earth's orbit and you want to come back into the atmosphere, we've got a deorbit burn, and that reduces the velocity of the spacecraft in order to re-enter the Earth's atmosphere. So we've explained the problem, we've talked about the maths, and we've outlined the technology. But the question is, have we actually managed to do it? So ADRAS-J is an astroscale mission that's currently in orbit, and it will be the world's first attempt to safely approach and characterize an existing piece of space debris. And it's the start of a fully fledged debris removal service. So this mission involves rendezvousing with an unprepared and uncontrolled piece of Japanese rocket. And the mission's ongoing, but we have to this point demonstrated all of the technologies that I've mentioned so far. We've planned safe trajectories, we've avoided bits of debris, we've determined the relative position of the client with respect to ourselves using angles-only navigation, and we've caught up to the debris using multiple maneuvers. So what you see here is an image taken by our spacecraft of the client in space from several hundred meters. And this is it from 50 meters. So this is from a position called home position, which is the final position before we would begin to try and catch that bit of debris. And I'll hopefully have a video that shows the client at 50 meters. So you'll sort of see it a little bit better when we come into the sun. But this is a really exciting mission to be a part of because Astroscale is the first company to attempt to do it. And we've done well so far. As you can see, we've managed to catch up with it. And hopefully this is now paving the way for Astroscale to become at the forefront of in-orbit servicing and active debris removal. So by learning about where maths is applied, both in the world around us, in our everyday lives, but also in the bigger global issues, we can change the narrative that we saw earlier, that maths is boring, that it's useless, and that it's not for everybody, and introduce fun and interesting ways that people can interact with it, and showcase that it has endless applications, making it an option for anyone with a passion for solving problems and making a difference. Thank you for listening.
We do have time for questions, if you're okay for people to ask questions.
Yeah.
Yeah.
So thanks for the really fascinating talk. If I remember correctly, the Russian and U.S. satellites that collided, I think people, the scientists that were watching it thought they wouldn't collide, but then they did collide. Is that true? And if so, is it because they had their uncertainty measurements incorrect, or what?
It's a great question that I don't have the answer to. I was not aware that we did not expect them to collide, but due to the difficulties in probability collision calculations, I can imagine that it would be the case that it was hoping that we would pass that by, and it didn't happen. I know from our own experience, when we're trying to figure out if we're on a collision course with anything, we're not going to get it's not a certainty that you're going to hit it, you're going to get a number. It's going to say the probability of collision is 10 to the minus 4. And actually 10 to the minus 4 sounds pretty small, but that is the probability at which we think, right, we need to look a bit closer at this. So you really have to account for a whole range of collision probabilities in order to be as careful as possible.
Cool. I don't have any questions, so please, somebody else. There's somebody at the back. Go ahead.
Thanks for the talk. Early on when you were introducing the orbital paths, you were talking about uncertainty of the trajectories. Mm-hmm. Does that impact how you try to do this interception process, the decisions you make about what maneuvers to do?
Yes, exactly. So we want to be as precise as possible, and we use lots of different ways to try and improve our knowledge of the trajectory. So when we're far away from the client, for example, we'll use a lot of ground-based measurements. So we've got things tracking us from Earth. So they can help say, well, this is where we think you are and where we project you to be. We'll also do our own calculations and say, well, from GPS, we know we're here. And with our own models, we predict that we'll be here. And we try and incorporate all of these different models and all the different uncertainties to give us the best possible picture of where we could be. But when we get close to the clients, it becomes particularly tricky, because when we're so close, the ground-based tracking doesn't work so well, because it can't really differentiate us from that bit of debris. So we really rely on our own models and our own calculations to make sure that we're safe.
Thanks. Hi, thanks again. That was a really nice talk. I have two questions. One of them was, is the delay in communication a problem at this scale? I mean, I don't know when that kicks in, how far away you have to be from Earth for that to be an issue. And the last question was, once you catch it, what are you going to do with it?
Two great questions. For the first question, the delay isn't so much of an issue. We rely upon ground passes, so we can't communicate with the satellite at all times. So there'll be a large portion of when it's in orbit where you're just relying on your predictions and thinking and hoping you're there. And you use your predictions to inform ground stations. This is when I think I'm going to be passing over. Can you please check, see if I'm there, and downlink all of my data so I can understand. And then when you get very close to the client, things eventually become autonomous, and then ground control is no longer our job, and we kind of have to rely on the onboard software to be able to more accurately calculate positions. And in terms of what we'll do with it when we catch it, so for this particular mission, we want to remove this from orbit. So we'll catch it and pull it into the Earth's atmosphere, and together with our own craft, we'll burn up. So that will become no longer an issue. But going forward, we're hoping to also develop some in-orbit servicing technologies, which would mean fixing broken satellites and be a multi-purpose craft. So it's not a one debris and done job. We would try and solve multiple pieces of space debris issues. Yeah.
On a different topic, can you say a little bit more about the Mathematicals series? I mean, there are a million things I'd like to ask you about it, but maybe like the process of what got you started and what goes into choosing topics, and how you make the videos and how you get the word out about them, and everything.
Thank you. Yeah, so Mathematicals, it was sort of came out of our PhD. So I studied at Oxford with Jess, the other Mathematical, and when we were at Oxford, we found that there was a great underrepresentation of women within the faculty and within the graduates. So undergrads were some like 50-50 girls and guys, but once you kind of got to that higher level, the numbers started to dwindle, and we would ask ourselves why. And one of the things that we really came up with was sort of discouragement from early stages. So this idea that maths is a boy subject, or not for girls, or girls aren't good at maths. And you see that in the media, and you see that kind of all over. There's just this little implicit bias that kind of is grinding in on us, and we're not even fully aware of that. So we wanted to kind of try and tackle that problem, and also simultaneously tackle the problem of maths being boring, because that's something we wholeheartedly disagree with. So we came up with Mathematicals as an avenue to try and channel that passion and make videos and different sort of outreach material that would be interesting to everybody, from kids to adults, and just spread the word that maths is fun. And in terms of where we get ideas for our content, we kind of try and bounce off what other people tell us. So when people say, we think this is boring, or maths isn't useful here, we sort of use that as fuel to try and prove them wrong.
When you're cleaning up space debris, I think you mentioned that you're focusing on the larger stuff. Certainly, it seems that way if your satellite's grabbing it and pulling it suicidally back into the atmosphere with it. What are the challenges for cleaning up the small stuff, and how is that different?
That's a great question. That can be trickier because we can really, at this point, only try and clean up things that are tracked. And now I did mention there's a lot of things that are tracked, and small objects are tracked. But our focus at the minute is sort of the larger bits of debris as a starting point, because they're easier to track. They're probably a bit easier to catch in terms, some of them already have things like docking plates that we're going to try and make use of in our own spacecraft, develop technology that is already going to be quite compatible with those bits of debris. But it's a great question and something that also needs to be thought about.
Cool. So I'm interested in optimization, and I noticed the maneuvers that you had, there were only 4 maneuvers. So this seems like if you were driving a car, you can only drive at 20 miles an hour, 45 miles an hour, or you can brake or something. So it's a very limited amount of maneuvers. Is there room for doing some optimization there where you maybe save some energy and do more intelligent maneuvers?
Yeah, absolutely. Yeah, so the maneuvers that I listed there are just some examples of different maneuvers that do exist.
Yeah.
But throughout the mission, we have executed a plethora of different maneuvering techniques. And that's one of the things that's been quite exciting about being involved in the mission, is trying to optimize the maneuver profile in order to save fuel and kind of catch up with the client in both the safest but the most efficient way.